Hello, Nishikant.
Yes, sir.
So you were there in previous session last week?
No, 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 sir. I'm
Okay,
first time.
okay, no issue. So you can see in the messages there is a link for video session for the video of previous session. Then there is this PDF of questions and solutions
Oh,
that were to be discussed in previous session. Some of them are pending. I'll discuss them this time. And there is this live session notepad also attached in the messages.
oh,
So you can access all those from these links given in the message box.
okay, sir.
We will wait till 5 minutes past 6 so that others also join.
Okay, okay, sir. No problem.
So, okay, so it is 6:05 now, and we'll start with the session. So this is right now the second live interaction session. In the first live interaction session, we what we actually discussed was we had this set of questions. Like the first question was, am I audible? Hello?
Yes, you are audible, sir.
Yes, sir. Yes,
Yes,
sir.
you are audible, sir.
Okay. So I should share my entire screen, right? You can't see the PPT. Now you can see the question, right? You can see the question slide.
Yes, sir.
Okay. So this was the first question which was being discussed. So in this case, what we do is we have this stiffness in the truss combination, and this is the connected mass, the lumped mass. So if we pull this mass down, what is the equivalent stiffness experienced through this system if we have this value K? So what we did here was we took this four linkages. We took this, sorry, we took these four linkages which were of equal length, and we used this delta B compression in the spring to analyze the delta L extension. And for that, we made an equivalent construction diagram, which is OAB. And we used the simple Pythagoras theorem, nothing special regarding that. And using that, we actually got the relation of delta B and delta L, which was L by B. And using the energy conservation, we found the K equivalent. So this is actually what we were trying to achieve. We wanted to simplify this whole this whole spring system into a simplified spring mass system, and we were finding the K equivalent for the same. So in the second question, actually, what was given in the question is, if there is this cart which is being pulled by the tractor, and the base is bumpy, like it is more like a rural road type of system. So we wanted to analyze that. The first part was to draw the schematic representation of the system and to finally form the governing equations. So for that, what we modeled was there was this equation of motion. We know the speed. So we can know the motion of this tire in the vertical direction, which came out to be x naught sine of omega t, where omega is lambda u naught. So uh, you can see the solution as well as the previous PDF slides. I have attached both of these PDF in the message box. I have given links, the drive links. And if you are unable to access, you can check it right now. If you are unable to access or there is some permission problem, you can tell me and we can directly sort it out. And then there was this, finally, we have the spring mass system where there is base excitation, we have stiffness, mass, and the finally the governing equation was formed. And the final governing equation was of this form. And later on, what we wanted to know is the second part, which says finding the maximum amplitude of vibration experienced by the equipment. So for that, what we do is we assume that excitation is of the form of y e raised to power j omega t. We substitute that and we form this relation. This relation, if you have gone through the lecture slides, the faculty actually discusses this relation, the professor, and this is the common relation we obtain. And finally, this is the expression we get. This capital omega is the ratio of excitation frequency to natural frequency. Obviously, the amplitude of vibration goes maximum, that is infinite, if omega is capital omega is actually equal to 1, which means that the excitation frequency matches with the natural frequency. So that is the usual theory we know, right? So, and the third part says the damping coefficient for the system to limit the vibrations within 30% of the damped vibration amplitude. So in that case, what we do is we equate this zero point 0.3 times that previously obtained maximum amplitude with the new amplitude obtained after adding damping coefficient. So using this equation, equating these things, we obtain the damping ratio. The damping ratio comes out to be this expression, and damping factor comes out to be this value. So here we actually stopped our previous lecture. So if you see this expression actually, what this expression says is zeta is equal to 1.59, sorry, 1.59 mod of 1 minus omega square upon omega. So if omega tends to 1, that is, if it is very close to resonance, then this particular, I'll just use this red color. So this expression, this top expression, it is very close to 0. 1 minus omega square is tending to 0. So with very small value of damping, we can obtain the 30% decrement. Like if omega is nearly equal to 1, this implies that with very small value of zeta, we can limit the 30% goal of amplitude reduction. But if capital omega is nearly equal to 0, then if we see this expression, this lower value will become very small. This upper value will become nearly equal to 1. So this implies that zeta will be much, much larger than 1 for same 30% amplification, amplitude reduction, sorry, 30% amplitude reduction. So that means if zeta is nearly equal to 0, if omega is nearly equal to 0, that is this omega is equal to omega by omega n, small omega by omega n. The excitation frequency is much lower than the natural frequency. Then we have to add a much larger damping. But if you have seen the lectures, this is actually called as stiffness dominated region. So actually, instead of adding damping, if we introduce the changes in stiffness in the system, we can very easily reduce the amplitude. And the third case is if omega is much, much greater than 1. So what will happen here is this above term will go much beyond the actually value. So if omega is very, very large than 1, then this implies that theta is also much larger than 1, which means that 30% amplitude reduction will be obtained by adding much larger damping. And this region actually corresponds to the inertia domination. So here, this, sorry, here the frequency of excitation is much larger than the natural frequency. So this is inertia dominated region, which means that adding a small mass to the system will actually have a much higher impact than actually adding a damping. So if you remember the class, then it was this type of figure. This is x naught, or the amplitude of vibration. Let's just say it as capital A, and this is omega, and this line here is omega n. So this region is actually called damping dominated. Which means that if our operating range is in this region, we can actually control the vibration much more efficiently using damping. If we are in this region, this initial omega much less than omega n region, here it is called stiffness dominated. So it is much easier to control vibration using change in stiffness. And in the much higher frequency range, we can actually call it as mass or inertia dominated region. So that gives a pause to our next part. Actually, this fourth part is slightly technical, slightly difficult. So here there is another vibration controlled. Sorry, I'll use this black pen. This was our original system, right? This base was excited as x naught sine of omega t. This is k. This is m. So what we want is, we want to add a tuned mass, which is m1, with stiffness k1, so that if the vibrations are at near natural frequency, or whatever the frequency is, we'll later look into that, whatever the frequency of excitation is, at that particular excitation frequency, the amplitude of vibration of this central mass is negligible. We don't care about this mass. This mass can vibrate at much higher amplitudes, doesn't matter. But this mass has to be at rest. So how will we approach this? What we will do is, we'll first make the governing equation. So here we will make this, sorry, this is x naught sine of omega t k m. This is k1 m1. So if we make a free body diagram for m, so if we assume that the velocity, displacement, and acceleration all are in upward direction, actually we write it as y. The vertical direction is y. So we have a downward force of my double dot. And if we assume that the spring force is downwards, then this first spring k, it has to get expanded so that the force is downwards, right? So for expansion, we assume that if this displacement is y, this displacement is y1, what we assume is y is greater than x naught sine omega t. So y minus x naught sine of omega t. This will be the extension, and multiplied by k will be the downwards acting force. And then there is this third force due to k1. So if this k1 force is downwards, we are assuming that still y is greater than y1. So here we write it as y minus y1. And these total resulting forces are equal to F, right? which is, by the way, 0 here. So what we can write here is, for the lower mass, my double dot plus k into y minus x naught sine of omega t plus k1 y minus y1 equal to 0. So if we use the lower mass m1, so for m1 it will be same, the inertia dominated force my1, sorry, okay, m1 y1 double dot. Double dot stands for second derivative in time. So y1 double dot is actually acceleration. And same for k1. If we assume that k1 is applied downwards, then in this case, we are assuming that it is an extension. So we assume k1 into y1 minus y. And again, the force here is again 0. There is no external force. So m1 y1 double dot plus k1 y1 minus y equal to 0. So these are the two equations obtained, right? We are clear until this point, right? Or should I go slow?
Yes, this is clear.
Okay, so we can move forward. So we have reached the limit, I think. So I'll just add a new slide. Okay, so what we had obtained was my double dot plus k y minus x naught sine of omega t plus k1 y1 minus y equal to 0. Then m1 y1 double dot plus k1 y1 minus y equal to 0. There is a mistake in this equation. Can anybody point which mistake is this?
I think y minus y1.
Yeah, exactly. So it will be y minus y1 in the above equation. And if we write it in matrix form, we can write it in matrix form, the above equation. It will be m0, 0, m1, and the vector will be y double dot, y1 double dot, plus this will be k. Actually, what we will do is we transfer this term actually uh, to this side. We write it as k x naught sine of omega t, and we cancel it from here. So what will be left here is k plus k1 into y, and here is this minus k1. In the lower term, it will be minus k1 and k1. This will be y1 is equal to, sorry, k x naught sine of omega t and 0. So can you agree on this matrix form? If you open the matrices, the above row will give the first equation, the lower row will give the lower equation. You can check it. Can we move forward? We can move forward, right?
Okay, no problem.
Okay. So this sine omega t can be written as e raised to power j omega t, and we just have to take the imaginary part in the final solution. So we can write the above equation, the forcing term actually, as k x naught e raised to power j omega t and 0. So if this is the forcing term, we can write the approximate solution term as y y1 e raised to power j omega t. This is the same thing we do in the this usual form, this single degree of freedom equation system. So if we substitute that, what we will get is m0 0 m1. There will be this minus omega square here, and this will be capital Y y1 plus of k plus k1 minus k1 minus k1 k1, and here we will be having y y1. Here it will be e raised to power j omega t, e raised to power j omega t is equal to kx naught 0 outside e raised to power j omega t. I'll just write it somewhere outside e raised to power j omega t. So we can cancel the e raised to power j omega t from everywhere, because e raised to power j omega t cannot be 0. T can never be minus infinite or omega, the frequency of excitation. So there is no way e raised to power j omega t is going to be 0. So we can cancel it from both the sides. We can multiply minus omega square inside the matrix, and we can take y and y1 vector as common. So this final matrix will become k plus k1 minus m omega square. This will be minus k1 minus omega square into 0. This will be minus k1 minus omega square into 0. This will be k1 minus omega square into m1. And this will be y1 is equal to k x naught 0. So this will be 0. This term will be 0. And these two terms are remaining, right? So what we finally do is, we can if we call the if we write this final form of this matrix, it will be k plus k1 minus m omega square minus k1 minus k1, and this is k1 minus omega square m1. This is the above matrix, right? If we take the inverse of this matrix and multiply to this side, this matrix will get transformed to this side, and we can get the y and y1 amplitudes, the maximum amplitude of the two masses. And then we can minimize y, right? That is the procedure to be followed. So what we do is, we take the inverse of k plus k1 minus m omega square minus k1 minus k1 k1 minus m omega square. So first we take the determinant, say d. What is d? D is nothing but k1 plus k, sorry, this will be k, k plus k1 minus m omega square multiplied by k1 minus omega square m1 and minus k1 square. So in case of this inverse, what we do is, we take the adjoint. So this term will go here, this term will go here, this term will go here, this term will go here with a negative sign change, and then transpose. So anyway, this can be written as the, if we say this as K matrix inverse, it can be written as 1 by D multiplied by K1 minus M omega square K1 K1, K1 plus K minus M omega square. So here it is M1. Oh, okay, I have missed here. From where I'm missing? Yeah, this one is correct. So it should be M1. So we have it correctly. So this has to be multiplied with Kx naught and 0. So this 0 will be for the second term, Kx naught will be for the first term. So what we get finally is we get the K1 minus M1 omega square into Kx naught and K1 Kx naught as the vector and multiplied by 1 by d. So this will be equal to y and y1. So if we go to the final response, so we can write capital Y as 1 by d Kx naught into K1 minus M1 omega square and Y1 as 1 by d K K1 x naught. So what will happen here is this thing, this above thing will be minimized. So we have to minimize this. The easiest way is to make this thing as 0. So this thing will be 0 when K1 minus M1 omega square is equal to 0, or omega is basically equal to square root of K1 by M1. And if omega is equal to K1 by M1, then what is D equal to? If you see, this term goes to 0, then D is only left as minus K1 square. So if D is minus K1 square, then Y1 is basically minus Kx naught by K1, right? And Y is approaching to 0. So what it physically means is, if we have this system where this base is getting excited at x naught sine omega t, this is k, this is m, this is k1, this is m1. If this excitation frequency is equal to the resonant frequency of this system, resonant at omega, sorry, resonant at omega, then whole of the excitation will get shifted to this upper system and no vibration will be received by the central mass. So this is what we call the tuned mass vibration control. But actually, if you see, for obtaining, if we see y1, it is equal to kx naught by k1. So this k1, if omega is constant, then k1 by m1 is equal to omega square, right? So k1 is proportional to m1 if omega is constant. So y1 will be inversely proportional to m1. So actually, we have to use a very large mass, so that this actually this y1 remains in control. That is why most of the times the tuned mass is used with a damper. Like we place a damper here so that even the resonant frequency vibrations are controlled. So tuned mass damper system is what we usually use. So we go further. Then this is the same system. Uh, we have this equipment at rest. The same. There is this same equipment which was initially moving and there was base excitation. Now what we say is the equipment has come at rest and there is a forcing, harmonic forcing that is going on. So what will be the, sorry, what will be the excitation? or the schematic of that particular system. This system is at rest. This is K, this is M, and there is this force F naught sine of omega t getting applied. So this is the simple spring mass system with equation my double dot plus ky equal to F naught sine omega t. So this is the usual spring mass system. And if we want to calculate for maximum amplitude, which is the second part, find the maximum amplitude of the vibrating equipment, it will be much simple than the previous system, because here we can simply say that F naught e raised to power j omega t is the excitation, and then we can write it as small y is equal to capital Y e raised to power j omega t, and we can simply say minus omega square m capital Y plus k capital Y common e raised to power j omega t is equal to F naught e raised to power j omega t. So this implies that capital Y is equal to F naught upon k minus m omega square. So if we simplify it even more, capital Y is F by k, F naught by k upon 1 minus omega square by k by m. K by m is nothing but square of natural frequency, and omega by omega n is nothing but capital omega. So F naught by k upon 1 minus omega square by omega n square, which can be rewritten as F naught by k upon 1 minus capital omega square. So if you see this, this is the almost similar expression obtained in the previous one, the previous B part. And using this, the third part, which is the same as reducing vibration amplitude up to 30% value. So this will be identical as the previous part. So now we will go forward with this week's content actually. So this fourth question is something I would like you to try first. There is a solution attached. I'll give the link in the description as well. But for now, what I want you to do is, I want you to note this question. I'll be adding the PDF of this question, but I want you to try this question first. If you are unable to do it, we'll again, we can discuss the next time. The second question is, which is actually similar variation, standard linear solid, has been discussed in class, but that is something I think most of you will find a little bit difficulty in understanding. That is why I am discussing the another one, which is not derived in the class, standard linear fluid. We'll be discussing here, and after you have known these two models, you can actually model the generalized Hooke's law for any standard system. So what we are talking about here is, when we talk about Hooke's law, usually what you have studied is sigma equal to E epsilon, but this is the linearized Hooke's law. A generalized Hooke's law says A naught sigma plus A1 sigma dot plus A2 sigma double dot and so on, An sigma n. So this is equal to B naught epsilon plus B1 epsilon dot plus B2 epsilon double dot plus so on up to Bm epsilon mth derivative with respect to time. So what we want to say here is, if in case we have a solid, then for a linear elastic solid, what will happen is, in this case, A naught is 1 and B naught is E. So what will happen here is, uh, all the actually rest of the AI and BI are equal to 0. But in case of fluid, what happens actually is, sigma is equal to mu into epsilon dot, if I'm not wrong. So there is actually a strain rate associated. It is not exactly mu, it is some C, or basically a new viscosity tensor or something like that. So it is not it is this type of relation. So here actually B naught is equal to 0, but B1 is actually equal to C. So this type of variations are always seen. And now what we discuss in class is we discuss the viscoelastic materials. So what they say is the viscoelastic materials are somewhere in between solid and fluid phase. So that is why we need to do that. We need to study it using that complex generalized Hooke's law. So we know the expression A naught sigma plus A1 sigma dot plus A2 sigma double dot dot is equal to B naught epsilon plus B1 epsilon dot plus B2 epsilon double dot and so on. So just for simple elements, like what they do is they model this particular phenomena using the spring mass system. Like what happens in a viscoelastic solid is if you pull it instantaneously. So the viscoelastic solid does not show an instant response. There is a delayed response. Like if you pull the solid, like this is sigma and epsilon, this is sigma epsilon curve. So what happens here is the stress strain actually goes fast, and then there is a relaxation. Like if there is a beam, you pull it instantaneously, then this expansion will happen after some time. So these are called creep and stress relaxation. So these type of materials are modeled using this SLS and SLF model. There are a lot of models, but you can find the details in the lecture. So here we will only discuss this SLF model. We will derive the generalized Hooke's law for this type of model. So we'll draw the model here. It says that there is a damper, there is this spring and damper in series, and this is the, if this is fixed part and this is forced part, this is sigma comma epsilon. So sigma shows the stress that is applied and epsilon shows the strain that is obtained. So first we'll go individually. So for spring element, individually for spring element, what happens here is the, if there is this spring element, it is fixed here and this is sigma applied. So it will instantaneously move to that direction, right? So this sigma is equal to E into epsilon. Let's just say the elastic constant of this particular member is E. It behaves like a beam, right? So if this is a beam, it is fixed from this and it is pulled from here. So if this is the material and it has no viscosity in it, so this beam material will simply extend instantaneously. So sigma equal to E epsilon is what we will be using for this relation. And if it is filled with purely with fluid, what will happen here is there is this piston that is getting pushed. So sigma will be equal to C epsilon dot. Actually, it is not C. In lecture, we use the term loss factor, which is eta, eta epsilon dot. So we know for spring element, it is sigma equal to E epsilon, and for damper element, it is sigma equal to eta epsilon dot. So these are the two expressions. So moving forward, if we make it as vertical configuration. So this is the damper, this is the spring, sorry, and damper configuration. This is fixed here, and this is pulled by sigma comma epsilon. So this is a parallel combination. So whatever extension will happen at this point will happen at this point. So these both the branches will have same extension, so same strain. So if we call it as branch 1, the epsilon 1, and this branch has strain epsilon 2. This element has strain 2 comma 1. Actually, I don't write comma. Epsilon 2 1. This has strain epsilon 2 2. Same goes for stress. This has sigma 1, sigma 2. This has sigma 2 1 and sigma 2 2. So we can write that due for parallel combination, what we will do is we will have sigma is equal to sigma 1 plus sigma 2. Just like forces, the stress also add up. So stress in this branch and stress in this branch will result in total stress in this branch. We will say this is equation 1. And for strain, epsilon 1 is equal to epsilon 2, which is equal to the resulting strain epsilon. And for series combination, the forces are equal in the branch. So are the stresses. So sigma 2 1 is equal to sigma 2 2, which is by the way equal to sigma 2. And epsilon 2 is basically the summation. So whatever extension happens here and here will be adding up in the total branch. So epsilon 2 is equal to epsilon 2 1 plus epsilon 2 2. So this can be said as equation 2, this as equation 3, this as equation 4. So we'll keep that in mind. So now the if we take for individual elements, for sigma 1, this element can be, we can say that sigma 1 is equal to eta 1 epsilon 1 dot. For this 2 1 element, it is a spring element, so we can write sigma 2 1 is equal to E epsilon 2 1 dot. So what we say is this has loss factor eta 1, this has loss factor eta 2, and this has spring stiffness K. Sorry, this has elasticity E. So what we can say for 2 2 is sigma 2 2 is equal to, okay, this will not be a differential. We can write it as eta 2 epsilon 2 2 dot. And now we take Laplace transform of this equation. So what will help here is, because these are differential elements and these are linear set of equations, so solving them in a linear and non-differential form will be much easier. So that is why we are taking the Laplace transform to convert it into linear equation. Sigma 1 equal to eta 1 s epsilon 1. We will use bar for the Laplace transform. Sigma 2 1, sorry, sigma 2 1 bar is equal to E epsilon 2 1 bar, and sigma 2 2 bar is equal to eta 2 epsilon 2 2 bar and S. So what we know here is epsilon 2 is equal to epsilon 2 1 plus epsilon 2 2. So we will substitute the values from here. We can write it as sigma 2 1, we are taking the Laplace transforms. So these are linear equations, so it won't matter. The Laplace transform is same as the equation. So sigma 2 1 upon E plus epsilon 2 2 becomes sigma 2 2 upon S eta 2. But we know from here that sigma 2 1 is equal to sigma 2 2 equal to sigma 2. So using that relation, we can again write it as sigma 2 bar as 1 upon E plus 1 upon S eta 2. So this epsilon 2 bar can be seen as this value. So we will write it again. Epsilon 2 is equal to sigma 2 bar actually 1 upon E plus 1 upon S eta 2, which can be further simplified as S eta 2 plus E upon S eta 2 E. And we know that epsilon 1 is equal to sigma 1 upon eta 1. S, right? From this relation. So here we can simply write that sigma is equal to sigma 1 plus sigma 2. We take the Laplace transform because if it is an algebraic equation, it won't matter. And we can directly write that sigma 1 from here is eta 1 into S epsilon 1 plus sigma 2 from here is epsilon 2 bar S eta 2 into E upon S eta 2 plus E. So we know from the relation that epsilon 2 is equal to epsilon 1 equal to epsilon, right? So we can use that to write as eta 1 S plus S eta 2 E upon S eta 2 plus E epsilon. So we have this actual stress strain relationship now. So now we can write this sigma bar is equal to eta 1s plus, sorry, eta 2s upon eta 2s plus E, and here we have E epsilon bar. So taking the common LCM here, eta 1 eta 2 s square plus eta 1 E s plus eta 2 E s upon eta 2 s plus E total in epsilon. So we take this term to the other side and we can write eta 2 s plus E into sigma bar is equal to eta 1 eta 2 s square plus eta 1 plus eta 2 into s E whole term with epsilon bar. So here if we disintegrate this, eta 2 s sigma bar plus E sigma bar is equal to eta 1 eta 2 s square epsilon bar plus eta 1 plus eta 2 E s epsilon bar. So we take the inverse Laplace transform now. So with the differential, we multiplied s, and if we are taking inverse Laplace transform, so for each s there will be one differential added. So here we can write eta 2 sigma dot for this term plus e sigma for this term, then eta 1, eta 2, epsilon double dot for this term, and eta 1 plus eta 2 e into epsilon dot for this term. So actually, we can simplify it even more, plus eta 2 upon e. This is just rearrangement, nothing fancy about it. Eta 1 plus sorry, eta 1, eta 2 upon e epsilon double dot plus eta 1 plus eta 2 epsilon dot. So this is the final expression where a naught is equal to 1, a1 is equal to eta 2 upon e, b naught is equal to 0, b1 is equal to eta 1 plus eta 2, b2 is equal to eta 1 eta 2 upon e. I hope I have done the derivation correct. Let me just check the values. Yeah, they are correct. So this is the final derivation, and this gives a closure to what we call the standard linear fluid model. So here what we do is we have a particular extension, and we know that for viscoelastic material, the stress and stress rate, strain and strain rate, all are actually variables. So right now we have just derived why they are variable and how they are related.
Sir,
Yes.
uh, sorry to interrupt you.
Okay, no
How
issue.
AB equal to 1?
In which slide? The previous one?
No, last one, this slide. AB equal to 1 or BA equal to 0, B1 equal to eta 1 plus eta 2. How you got
This
these values?
I'm using this expression.
Okay, okay, fine.
So this is the actual expression. Even if it comes in the exam, you will be assumed that you know this form, that A naught sigma plus A1 sigma dot plus A2 sigma double dot so on is equal to B naught epsilon plus B1 epsilon dot plus B2 epsilon double dot so on. This is the generalized Hooke's law. It is covered in the lecture slides, and any real material has all these coefficients, and if these coefficients are constant, then it is called a viscoelastic material. And this second week lectures mostly deal with that only, the derivation regarding viscoelastic material. So one of the primary thing to remember is always if you are given the standard linear solid model or standard linear fluid model or any such similar model, like if this is the model given to you, what is expected from you is, if this is the model explaining the stress and strain relationship, what is the generalized Hooke's law that governs this system? Because finally what we want to do is we want to approximate the material behavior, right? So if we know A naught, A1, A2, B naught, B1, B2, and so on, and from this expression, this derivation, we know this A naught, A1, B naught, B1, B2 value, then we can tune the this loss factors eta 1 and eta 2 and this elasticity E, so that it can actually approximate the original material we want to design for. You are getting the point?
Can you repeat, please?
Yeah, I can repeat. Just we'll go to the new slide. So we have a generalized Hooke's law, right? And that is of the form A naught sigma plus A1 sigma dot plus A2 sigma double dot so on equal to B naught epsilon plus B1 epsilon dot plus B2 epsilon double dot so on. So this is the generalized Hooke's law, right? And for any material, any given material, we can have A naught, A1, A2 so on, B naught, B1, B2 so on values. These are given or experimentally obtained, right? But we can't actually model these equations directly. It will be too much computational effort and too much effort if someone wants to just get an approximate model or just want to do some quick calculation. So solving these equations directly is not always a very good solution. So what people do is they approximate using this system. This is one of the example system which is called SLF, which is the standard linear fluid. What they do is they use this damper spring and damper element. This has loss factor eta 1, this has loss factor eta 2, and this has elasticity E. And what they do with that is they actually get these values. These values. So if we write it here, A naught was found to be 1, A1 was eta 2 by E, B naught is equal to 0, B1 is eta 1 plus eta 2, and B2 is eta 1 eta 2 upon E. So we have these values. These are the relation. So this relates the actual material with our idealized system, which is one damper here and one spring damper here. So this is our idealized system. So what we do is we modulate this idealized system to match with the actual material using these elements. Am I uh, am I making sense now?
Yes, sir. Yes.
So this is what we try to do. Similarly, if you see the class slides, there is this standard linear solid model, SLS model, standard linear solid model. And there are many such other models you can try for practice. And if you see for standard linear solid, it is a similar derivation actually. Nothing fancy about it. You can simply derive it. And for same thing, we get A naught value, which is 1, A1 value, which is eta by E2, B naught value, which is E1, B1 value, which is eta E1 plus E2 upon E2. And the model is more like spring with spring damper. This is E1, this is E2, This is eta. Because why do we need multiple models? Because in this model, if you see B naught value is 0. So we can't use it to model any material which has a non-zero B naught value. For that, we have to go for standard linear solid. But the other drawback is here that B2 value is 0 here. So if we want a positive or negative or basically finite value of B2, non-zero value, then we have to shift to this SLS model. We have to replace it by damping. And there are many more much complex models than this model. We can actually use the much more complex four element models and more which have been covered in the class lectures, so that we can actually obtain the more good approximation of that actual material. So I'll just add the links for this question and solution thing in the message chat box. That is okay, right? So this one shows the questions, and for the solution, you can download it, and I'll be sharing the video link shortly. Actually, in between of the week, it is a little bit difficult, and I don't know if NPTEL guys will be sharing with you. So, and for the previous session, if you have missed the previous session, we can actually in the start of that message box, you'll see the links for the previous week's solution and the solution PDF and the questions PDF and the link for video as well. And for the video, that is a YouTube video, in the actually in the description as well, I have given links for the class lectures, because in last class, many people have not seen the lecture videos. You guys have seen the lecture videos?
Yeah.
Okay. And how did you find the quiz? Was it
Very
easy or difficult?
no.
So any doubts or any specific thing you want to ask regarding the lectures and all? So there are no doubts, right? Anybody?
No, thank you, sir.
Okay. So just as a hint, what I can tell you about the previous question is what we do is we have this problem in question 3, right? The simple spring mass system. So in that case, what we do is we use a rectangular cross-section bar, and we have a specified width and thickness associated, and we have a constant mass, a specified mass. So what we are left free with is the height of bar, which is variable, and we have to select a particular material based on that to optimize that particular uh, situation. So what we want to do is we want to optimize, as we know, we have to induce a maximum damping or the minimum vibration. So what we have to do is we have to design a figure of merit. Figure of merit is nothing but an expression. Basically, you have to derive an expression in which it deals with some of the variables, or actually the variables which you have to look for, the overall variable ratios which you have to look for while designing the material. So there is a problem given in the lecture as well, which deals with a beam with transverse loading. So for that, you can see the lecture there. There it is quite well discussed how to solve it for a beam. Right now in this question, what we want is we want actually a bar. It is not a beam, it is a bar. So in case of a bar, you have a axial loading, and that is why the equivalent stiffness also changes. So there is a small variation in the solution. If you are unable to solve it, we can discuss it in the next lecture. I think the time is up. So in the next live interaction, or if you want, I can continue actually. But it would be good if you try yourself. You want to give it a try yourself first? Okay, I take it as a yes. So thank you for joining. And now I'll be ending this session. Thank you.
Thank you, sir.
Thank you. Thank you very much.
Okay.